Okay, so when we look at this problem, we notice that we have a function raised to another function, and this gives us a hint that we are probably going to want to use our natural log trick coupled with L'Hopital's rule. And so remember what we do. If you did all the other ones, you remember, is that we call this guy, what we're looking the limit for, y, and we remember that e to the natural log of y is going to equal y. Okay, and so then what we do is we find the limit as x approaches 0, not of y, but of natural log of y. And when we find the limit as x approaches 0 from the right side of natural log of y, this allows us to bring down the exponent using the laws of logarithms. And so what I'm going to have is this is equal to the limit as x approaches 0 from the right of x to the, well, just x, sorry, times tangent of 2x. And then what I can do is I can bring the x down, so then I would have the limit as x approaches 0 from the right of tangent of 2x over x to the negative 1. Oh, sorry. I forgot I left the natural log out. So this is x times natural log of this guy, and then up here is natural log of this one. Sorry about that. Okay, so anyways, what we have here is the numerator is going to, well, tangent of 0 is 0, and if we're approaching from the right, the numerator is going to negative infinity, and the denominator is going to infinity, so this means I can use L'Hopital's rule on this one. Okay, so if I use L'Hopital's rule on this guy, what I'm going to get is the limit as x approaches 0 of the derivative of natural log of tangent of 2x. This is 1 over tangent of 2x times the derivative of tangent of 2x, the inside, which is secant squared of 2x times the derivative of the inside, which is 2. Okay, and all of this is going to be divided by the derivative of x to the negative 1, which is x to the negative x to the negative 2. Okay, and now if we simplify this a little bit, what we're going to get is this is equal to the limit as x approaches 0 from the right. On top, we're going to get 2, and this x to the, actually let me bring the negative sign up. The x to the negative 2, if you invert and multiply, it's going to end up on top positive. And then we have secant squared of 2x over tangent of 2x. Okay, and so if I plug in 0 here, well, I get 0 times secant, remember, is 1 over cosine, and cosine of 0 is 1, so on top I have just 0 over 0. But I can, you might be tempted to just use L'Hopital's rule here again, but notice that after, you should look for things that simplify. And so I don't know if this is going to lead me anywhere, but remember that secant is 1 over cosine So this is 1 over cosine squared of 2x. And then this guy is sine of 2x over cosine of 2x. And so I feel like changing these to sines and cosines and seeing if anything cancels out. So let me rewrite this. What I'm going to get is, so if I switch the secant squared for 1 over cosine squared, what's going to end up happening is I'm going to have cosine squared of 2x on the denominator. Okay, and now this one, if I invert and multiply, the cosine of 2x is going to end up on top, and the sine of 2x is going to end up on bottom. And so notice what happens is one of these cosines cancels with one of these. And so this is equal to the limit, as x approaches 0 from the right, of negative 2x squared over sine of x cosine x. Sine of 2x cosine of 2x. Sorry about that. Okay, and so I mean this is a lot simpler than the one that I just had, and but I still, when I plug it in, I get 0 over 0. So now if I use L'Hopital's rule here, I mean at least it's a lot simpler to find the derivative of this than as opposed to this one. So the derivative of the top this time is negative 4x over, here I have to use the product rule, so I'm going to have 2 cosine of 2x times cosine of 2x plus sine of 2x times 2 cosine of 2x. Sorry, I ran out of room there. But this now takes me somewhere, because if I forgot to write down the limit again. Limit as x approaches 0 from the right. Okay, sorry about that. This one is approaching 0. But this one, cosine of 0 is just 1, so this is just 1 times a 2. So this is really, the denominator is approaching, the whole denominator is approaching 2. And then the numerator is approaching 0, because, well, negative 4 times 0 is 0. So this limit is actually equal to 0. Okay, but then you have to be careful. Remember, what we just found is the limit of the natural log. So then I have to go back and use my property, and my answer is going to be not 0, but my answer is going to be e to the 0, which is equal to 1. And that's it. And this is our very last problem, and it's not necessarily the most difficult one, but you do have to be careful with this one. It's very easy to get this confused. You see this negative 1 right here, and you might be tempted to just say, oh, I can just move it down as a fraction, but you have to be really, 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 really careful, because although that seems simple enough, remember that this is notation for the arctangent of x. This notation is the inverse tangent of x. This doesn't mean tangent to the negative 1 power. That would be this. And this is equal to 1 over tangent of x, which in turn is equal to cotangent of x. And these two are very, very, very different. So you need to make sure that you don't make that mistake of confusing. These two are definitely different. Okay, so that allows us to get the problem started. Now here, again, what we want to do is first we plug it in, and we notice that the first one, this one's going to negative infinity. This one, the arctangent, or inverse tangent, if you forgot what it means, I discussed it in problem 7, so if you're confused with that one, go back to that one and look at the little explanation I had at the very beginning of inverse trig functions. But this says inverse tangent of 0, remember, means what angle is tangent 0 at? Well, that's 0. So this is negative infinity times 0, which means that this guy's indeterminate, and since it's infinity times 0, or negative infinity times 0, it doesn't matter, I can use my backwards tortilla trick that I've been using for several other problems. And it's really up to you which one you want to bring down. Sometimes you can tell which one's better. In this one, I guess it's not as easy to tell, but I think I'm going to, because the inverse tangent has a little bit more complicated of a derivative, I think I'm going to move the natural log down and leave the inverse tangent alone. So I'm going to move natural log of x down, so it's going to be natural log of x to the negative 1. Okay, so now what I have is 0 over 0, and so I can use L'Hopital's rule. And if I use L'Hopital's rule, what I have is the limit as x approaches 0 of the derivative of arctangent, or inverse tangent. Remember, you're supposed to memorize it. It's 1 over 1 plus x squared. Now the derivative of natural log of x to the negative 1, this is going to be negative natural log of x to the negative 2 times the derivative of natural log of x, which is 1 over x. Okay, so if I simplify this, what I'm going to get is negative x. If I do my tortilla inverted multiply, I'm going to get negative x times natural log of x, the whole thing squared. Oh, I did it again. Limit as x approaches 0. Sorry about that. Over 1 plus x squared. Okay, and now if I plug in my value 0, here I'm going to get 0. This one's going to negative infinity, so this whole thing is going to positive infinity. And this one is going to 0, so the denominator is 1. So the numerator is indeterminate, and the denominator is simply 1, and so I have to do some more work. And there's nothing I can do to simplify here, but what I can do is just leave the natural log there. Leave natural log here, and bring the x down as x to the negative 1. And then this would multiply 1 plus x squared. And so then if I just simplify a little bit more, what I get is natural log of x squared, over x to the negative 1 plus x to the positive 1, if I distribute this one down to both. Okay, now if I plug in 0, this guy's going to infinity, and the denominator x to the negative 1 is also going to infinity plus 0. So I have infinity over infinity, so this means I can use L'Hopital's rule again, and hopefully this will take me somewhere this time. So L'Hopital's rule, what I'm going to have is on the numerator, I'm going to have 2 natural log of x times 1 over x. And then on the bottom I'm going to have negative 1 over x squared plus 1. Okay, so now I can simplify this a little bit. What I'm going to have is the limit as x approaches 0 of 2 natural log of x over x all over, if I find the common denominator here and combine, I'm going to get x squared minus 1, so this is x squared minus 1 all over x squared. Okay, and then if I do my my tortilla here, what I'm going to get is this is equal to the limit as x approaches 0 of 2x squared natural log of x over x times x squared minus 1. And so then this guy cancels with one of these, and this is looking pretty bad because I have again 0 times infinity, and here in the denominator I have 0 minus 1, so I have 0 times infinity. But there is a little good news, is that if I'm not sure if this is good news actually. Well, let me try bringing the x down. So if I bring the x down, I would get limit as x approaches 0 of 2 natural log of x over x to the negative 1 times x squared minus 1. And if you compare that to what I had back here, this is almost exactly the same thing, and I just went through like 20 million steps. But we should at least maybe do one more, and hopefully this will get us somewhere. So let's take a look at what we have here. 2 ln of x over, on the bottom now I'm going to have just x. If I distribute the x to the negative 1, x minus x to the negative 1. Okay, now I have again infinity over infinity, and if I use L'Hopital's rule, I'm almost running out of room here. But we must continue. So the numerator is less complicated this time, so I'm just going to have 1 over x on the numerator as the derivative. Well, sorry, 2 over x, because the 2 that's right there, over 1, well, the negative comes down, so it turns into plus 1 over x squared. Okay, and then if I simplify the denominator into x squared plus 1 over x squared by combining the two fractions together, what I get if I invert and multiply, so I'm kind of jumping a few algebra steps here, but that's okay, I'm running out of room, I'm running out of paper. So I have the limit as x goes to 0 of 2 over x times, if I invert and multiply, I'm going to get x squared over x squared plus 1. And then this one's going to cancel with this guy, and what I get now is the limit as x approaches 0 of 2x over x squared plus 1. And phew, now if I plug in 0, what I end up with is 0 over 0 plus this 1, which is simply equal to 0. And now I'm done. So that was a very long problem, and I don't really know if I would have, at the very beginning we made the decision, or I made the decision, to move the natural log of x down to the bottom and do it that way. And maybe if we would have brought the inverse tangent down to the bottom instead, it might have been simpler, but it might have taken even longer or not even have gotten us anywhere. So you don't really know all the time. But I mean, in the end, after doing L'Hopital's rule 1, 2 times, and a lot of simplifying, we end up with our answer in the end. And now we're done.